And now the next chapter is about computation of integrals. Remember the formula, the fundamental formula of integral calculus that says that in order to compute an integral, what is also called a definite integral, you must know a primitive. And now remember that we computed derivatives for many functions, and now we want to reverse the computation that we made for integrals in the following way. We have here a table, and this is a typical table. You can find one table like that in all books of analysis 1. So here here we are basically with this table, and inside the column here we have a function f, and here we will write the derivative f prime, and here the indefinite integral. Okay, so let us start with a constant, which is probably the easiest function. So we have k in R. When you differentiate a constant, you find 0. When you integrate, when you find the derivative, you have to look for the function whose derivative is a constant. In order to do that, we go to the second function here. Consider x to m, where m is every integer number except -1. We already studied -1, so here we get as a derivative mx m minus 1. So as we already know, if m is equal to 1, this derivative is a constant. So here, in order to obtain kx when we differentiate, k when we differentiate, we must start from kx. But of course, the indefinite integral of k must depend by a single additive constant. So this is what we write here. So analogously here, using this rule and reversing it, we find that in order to obtain x to the m, we must start from x to the power m plus 1, and then divide by m plus 1, because when we differentiate this, we have x to the m times m plus 1. So to obtain just x to the m, we must divide by m plus 1. And then again, add c. In this differentiation rule, there is no x to the -1. So let here study x to the power -1. 1 over x. When we differentiate, we follow exactly the same rule here, which is which gives minus x to the power -2. But notice that we cannot integrate here in the same way, because if we apply this rule, -1 plus 1 is equal to 0, we end up by a constant. But if we differentiate a constant, we find 0. So this rule has to be changed, and by the exercise I gave you, you should know already that the indefinite integral of 1 over x is log of the absolute value of x. Don't forget about this absolute value. It is a mistake that I will punish very tough. Okay? Log of absolute value of x plus c. And then the next row is about, again, power, but not an integer power, an arbitrary power. So here we write x to the power a, where a is a real number. For every real number we must bound x to positive values, and again when we differentiate, the rule does not change with respect to integers, a x to the power a minus 1, and also for integrals it is always the same, so it is x to the power a plus 1 divided by a plus 1 plus c, and again a must be different from minus 1, in case minus 1 has already been treated. And now we go to function that we know very well, sine of x. When we differentiate it, we find cosine of x. So when we look for the primitive of cosine of x, it will be sine of x plus c. And when we differentiate cosine of x, we find minus sine of x. So here the primitive of sine of x will be minus cosine of x. Don't get confused with signs here. Then we go to hyperbolic sine of x. And here we get the hyperbolic cosine of x. And if we start from the hyperbolic cosine of x, we find the hyperbolic sine of x. So it is clear that for the primitive of hyperbolic sine of x, we must write hyperbolic cosine of x, and for the primitive of hyperbolic cosine of x, we end with hyperbolic sine of x. Everything plus c. And so now you can look for other. So here, okay, I think these are the simplest ones. So I stop here. This table you can find in book more sophisticated tables and so on and so on. And tables give you the sort of basis of knowledge starting from which you must be able to compute other integrals. And then in order to show how to use it, let us go with some examples of simple definite integrals. What we call just integrals are indeed definite integral of simple definite integrals. And so here we have the integral between 2 points a and b of x squared. You go to the table, x squared is here with m equal to 2, so you have x to the third power divided by 3. Here what you do is just to write here one specific primitive, and here the simplest one is x3 over 3. So here just write one particular. What does this primitive of particular to be particular? Absolutely nothing. Particular means that it is one among all primitives, one particular primitive. And here, evaluate it between a and b, and this is what one usually writes from a and b. So you have b cubed divided by 3 minus a cubed divided by 3. And you remember the computation that we did at the example in particular. It was the integral between 0 and a of x squared, and this was a cubed divided by 3. We already computed it using upper and lower sums, if you remember. Okay, and so another important example is the following. It is the integral between 0 and pi over 2 of cosine squared of x. These are, then here you have different ways of computing it, and simple way is the following. You rewrite this cosine square as 1 plus cosine of 2x divided by 2 dx. This is equal to pi. So let me write here. This is, we can use the algebra of integrals. So the integral of a sum is equal to the sum of the integral. So here you have the integral from 0 and pi over 2 of 1/2 plus the integral from 0 to pi over 2 of cosine of 2x divided by 2. Now the first integral, the integral of 1/2 is the integral of a constant. So here you have the integral of a constant. So you have 1/2 x plus c, but here just write 1/2 x to be computed between 0 and pi over 2 plus, and here you have 1/2 0 pi over 2 cosine of 2x dx. So here, of course, if you go to the table here and look at the integral of the cosine, you find sine. So you can be tempted to say that the primitive of cosine of 2x is sine of 2x. So, but we notice that if you start from sine of 2x and you differentiate it, you find cosine of 2x times 2, because it is a composition of function. Therefore, in order to obtain just cosine of 2x as a derivative, one must divide everything by 2. Indeed, if you start from 1/2 sine of 2x prime, then you find cosine of 2x. So this is a primitive. So, a primitive of the function cosine of 2x is not sine of 2x, but is 1/2 sine of 2x. Of course, there are various procedures in order to do that. And for instance, here, so you can proceed as follows. you can say that this is equal to 1/2, here we are, pi over 2 minus 0, plus 1/2, and then right here, in order to get your idea, you multiply by 2 cosine of 2x, then you have to divide by 2. And so here you immediately have that this is equal to sine of 2x prime. This is another way to recognize. So is just to, as you see 2 here, you notice that when the argument is 2x, then if you differentiate whatever function which is a function of 2x, you will obtain here 2. So you add 2 here, and then of course you have to divide by 2 here, so you can integrate directly the function here, because the 2 will be restored by the 2 here. This is another intuitive way, but of course there is another method which is more general, and just to tell you the various ideas that you can have in order to differentiate this guy here. However, from here we get pi over 4, and here plus 1/4 the sine of 2x, with x going from 0 and pi over 2. And this is pi over 4 plus 1/4 sine of pi minus sine of 0. Both of them are equal to 0, so we get pi over 4. Okay? So, and now we go to a more general method to integrate functions that are composed. So, more generally, there is a method, an algorithm, for integrating composition of functions. And this is called the integration by substitution. And so I told you about the method of integrating composition of functions. So remember the following rule of the algebra, that f of phi of x prime is equal to f prime of phi of x times phi prime of x. Then, integrating both sides, and also exchanging them, because we will put the right side to the left. Here you have the integral of f prime of phi of x times phi prime of x dx equals f of phi of x plus c. Okay? And, okay, concerning the definite integral, so this is for what concerns the primitive, but concerning the definite integral, one has the following computation. So you integrate from a to b, f prime of phi of x times phi prime of x dx. So one primitive is f of phi of x from x equal to a and x equal to b. And this is equal to f of phi of b minus f of phi of a. And this you can rewrite also as f of y between y equal to phi of a, y equal to phi of b. And so you write it like f of y dy between the extremes phi of a and phi of b. So this is the final formula you have to keep in mind when you compute a definite integral of a function which is a composition. Okay? I will give you some examples, and the first example is the following. So you have here e to the x, the integral of e to the x divided by 1 plus e to the power 2x in the x. Okay, how can you proceed? Okay, you can proceed as by saying that this is e to the x. This is very stupid remark. This is 1 plus e to the x to the squared in the x. Now you see that quite naturally there is a variable that arises here from this computation, because here you have e to the x, here again e to the x. So the natural variable here is e to the x, also because when you differentiate e to the x, here you find e to the x. So it seems that you are falling here in this scope by just replacing by the symbols in the following way. E to the x is phi of x, and this e to the x here you interpret as a phi prime of x. So in this way, here, you have this structure. Because you have phi prime here at numerator, and you interpret the function, just this function here, as the function to be integrated. But, however, to be clearer, the idea can be borrowed by here. You find y, you write y, or better here, y is phi to the x. So you have that y. So introduce the new variable y is equal to phi of x, which in this case is e to the x, and use the formula here, or better, but without the extremes of integration. And you find that this is just the integral, sorry, this was f prime. This is just the integral of 1 over 1 plus y squared in dy. Why there is no y here at the denominator? Because y has been absorbed here, has been absorbed in this way. Here there is no phi prime. In the new formula, phi prime has disappeared. It has been somewhat absorbed into the dy. Notice that there is no y at numerator. You can say morally or formally according to asterisk, the factor y, which is equal to phi prime of x, has been absorbed into dy, which is just a symbol, but everything goes as if this happened. Of course, there is a deep geometric interpretation of that, but for us, for the analysis one, it is just a sort of game of symbols. So, a practical way to perform this passage is the following. You have y is equal to phi of x, and then you replace by dy is equal to phi prime of x dx. In our example, y is equal to e to the x, so dy is equal to e to the x in the x. So, at the end, so therefore, our integral is e to the x divided by 1 plus e to the power 2x in the x, and all this is incorporated into dy. So you have dy, and then what you have to integrate is 1 plus y squared, and so the integral of this is of 1 over 1 plus y squared is the arctangent of y plus c. Remember the definition of y is e to the x, so you end up with the arctangent of e to the x plus c. Okay? This, the first time you do a substitution, you make a substitution of the variable here is somewhat complicated, but remember, integration is difficult. Differentiation is easy. So once you find the primitive, you can verify it. So, and to verify it, just differentiate the arctangent of e to the x. If you want plus c, but this is not important because when you differentiate a constant, you obtain 0. And so you have 1 plus 1 plus e to the x to the square, e to the 2x, then composition of function, you have to differentiate here, and then e to the x. And this is exactly our integrand here. And so, then you go another exercise with definite integral. And for instance here you can take the integral between 1 and, so to say, logarithm of 5, for instance, of e to the x 1 plus e to the 2x. This is equal, because we already know a primitive, this is equal to arctangent of e to the x between 1 and log of 5, so you end up with arctangent of 5 minus arctangent of e. But if we don't know a primitive, we are not obliged to compute it. because we simply have the following method. We start by 1 log 5 e to the x divided by 1 plus e to the 2x in the x. And here we use this replacement, y is equal to e to the x. So by asterisk, remember that here we rewrite dy divided by 1 plus y squared, but here the extremes of integration can be changed according to the replacement. So instead of ab here in the variable y, we use e, so e to the 1, which is e, and e to the log 5, which is 5. Now we integrate just this function here. We never use the variable x. Okay? Variable x has ended its role, and so here we have the arctangent of y between e and 5, and so again. At the end, we find the arctangent of 5 minus the arctangent of e. Good. Mm-hmm. So, and this is what we aimed at saying up to now. Just the last remark, at least for this video, and so an important remark is the following. Here, if you have, remember that integral of f of phi of x, phi prime of x, is equal to f 5 of x plus c. So it is quite important here to recognize that there is a phi prime. So therefore, you have that phi prime of x divided by phi of x dx. You recognize that here we have the inverse of a function phi, and here we have phi prime that more or less is linked to the x. So here you can immediately write that this is log of the absolute value of 5 of x plus c. Indeed, proceeding slowly by substitution, you can write y is equal to phi of x, so y prime is equal to phi prime of x. So again, dy is phi prime of x dx, and so here phi prime dx divided by phi is equal to dy over y, and this is log absolute value of y plus c, and this is log of absolute value of phi of x plus c. Okay, and then we will see other substitution in the